Long before we ever built complex thinking machines, we first had to figure out exactly how to observe and look at the world around us. When a child watches a shadow stretch across the dirt, or a farmer tracks the changing shape of a cloud, they are doing more than just looking. They are noticing repetition. They are spotting differences in their environment. This is a pattern. It is the functional bridge between the messy noise of reality and structured human thought. Noticing a single shadow is easy, but tracking thousands of them changing across different seasons, varying terrains, and many years exceeds what a single human mind can reliably remember. For these observations to become useful for a community, they had to be compressed into a shared record, something we could actually measure. Mathematics provides that exact tool. It allows us to take the physical world and translate it into data. This page shows how notation performs this task. Symbols like X and Y allow us to describe how any number behaves, capturing a broad relationship in a single line. This notation compresses millions of separate data points into symbolic structures we can manage. When we plot these compressed numbers onto a 3D coordinate system, abstract concepts, like a person's age or income, become specific coordinates. In this space, physical closeness represents relationship. If 2 points sit near each other, the math tells us they are semantically similar. If math can map the exact shape of reality, we have to ask, can we engineer a machine to navigate that space and learn from it? Imagine a sphere rolling down a contoured valley, blindly seeking the lowest point. This is how a model finds its way through a problem. As a machine navigates data, it isn't understanding the world. It is simply feeling its way down the slope, tuning its internal mathematical sensitivities to reduce its error rate. This pipeline outlines the operation. The system takes input, calculates a score, makes a decision, and measures its error. This improvement phase drives the engine. Feedback mechanically alters parameters to perform better next time. We label this behavioral adjustment learning. The machine adjusts its weights to hit a target, creating an output that looks intelligent, but operates entirely without subjective experience. When you scale these simple adaptation loops across massive datasets, billions of words and images, the resulting outputs mimic human logic with high accuracy. As we see in this text breakdown, even generating a smooth sentence is an exercise in geometry. The system represents words as vectors and calculates the highest probability for which word vectors should follow one another. This creates a cognitive blind spot. Humans have evolved to infer minds from behavior. When a machine speaks with perfect grammar and accurate answers, we instinctively project an inner life onto the code. Because these systems alter legal cases, impact medical diagnosis, and shift financial markets based purely on math, we must define their limits. The machine cannot bear moral weight. The responsibility rests with the humans who deploy it. These algorithms impact real lives. They influence who gets a loan, who receives medical care, and how our cities are built. A machine drinks patterns from a dataset, but it has no lived context. It relies entirely on us to supply the purpose for the work. This requires first principles thinking. Before a technological tool is used, we have to break the problem down to its core truths and define the ethical boundaries. Because AI is shared infrastructure, governing it requires institutional action. Organizations like UNESCO establish policies that protect data, labor, and human rights globally. Ethics is not a decorative layer added after a system is built. It is the fundamental boundary that protects human dignity and makes the tool legitimate. Artificial intelligence is a tool for processing noise. It handles the overwhelming volume of modern data so that humans can focus their energy on meaning. Machines handle the scale, but we retain the specific advantages of ethical judgment, taste, historical context, and mutual care. Mathematics and machine learning provide a language of structure. They allow us to navigate a world of data that is otherwise too complex for us to see clearly. A moment of wonder. These systems continue the process of noticing structure we began with a shadow, only now at the scale of millions of signals every second. To explore the complete collection of these foundational ideas and discover a new way of seeing the world, join us for the next chapter.